This series of presentations helps you understand what is happening behind the curtain when you use the web, email, or anything else through the internet. In this presentation, we get down to bits and bytes in Tcpip. Connections between computers on the internet are end-to-end. Two computers establish a connection and then exchange packets. Any computer on the internet can try to initiate this exchange with any other computer on the internet. The first three packets those two computers exchange are called the TCP handshake. More on that in a bit. The Internet Protocol says what the first 128 bits in each and every packet must be. That's called the IP header. It identifies the IP address of sender and the IP address of the recipient, among other routing information. After the IP header, the TCP header identifies the sequence number of the packet and contains a checksum to see if there are mistakes in transmission. Most packets carried over the internet follow version 4 of the Internet Protocol, but IPv4 addresses ran out, forcing the creation of a new protocol, version 6. The new protocol allows the sender to keep more information private. Most packets being sent on the internet are still using IPv4. For IP version 4, this protocol table of the IP header shows what the zeros and ones mean and in what order. Each row of the table describes 4 bytes. That's 32 bits. 32 zeros and ones. The protocol says to begin the transmission identifying what version of the protocol you're using. Version 4 in binary is 0100. Approximately 90 bits later come the to and from addresses. This packet is from a computer at IP address 255.1.1.1, for example. The sender's address is shown here in bits. 255 has all the bits on. The second, third, and fourth bytes of the dotted quad are all 1. Only the ones place in each byte is on. Can you explain why the recipient's address has all ones here? Okay, so the IP layer has the addresses. The Internet Protocol gets the packet to the right address. Remember, the protocols allow computers to use zeros and ones to communicate, compromises among speed, security, and so forth. Protocols climb the ladder of abstraction by taking care of distinct responsibilities. Addressing? Internet Protocol has it covered. You can put whatever you want in the body of the IP packet, and it'll probably get there. Now the TCP header, that comes next in the transmission. It doesn't have to worry about getting to the right computer. It worries about making sure that all the packets have arrived and that no mistakes were created switching ones to zeros. How does TCP do that? It starts with the TCP handshake. The TCP handshake uses the SYN-ACK 1-bit flags in the TCP header. These are each a single bit, a single 1 or 0. The names stand for synchronize and acknowledge. The TCP header also uses the sequence and alignment numbers that are each 32 bits. No one remembers these details. We look them up if we need them, but the concepts are useful. Notice these ports. The exchange is between a specific port on each computer. Port 80, as shown here, is used by web servers and web clients alike when sending or receiving HTTP packets, technically IP containing TCP containing HTTP data. The 3-packet TCP handshake is the beginning of any exchange of TCP/IP packets, not just web pages or exchanges between clients and servers, but all internet traffic, well, most of it. During the TCP handshake, both computers pick a random sequence number and send it with the SYN flag set to 1. As shown here, the other computer is supposed to respond to a SYN flag with a packet of its own, but with the ACK flag set to 1. And with an acknowledgement number, telling what data the acknowledger is ready for. So, SYN67 gets acknowledged with ACK68. In the very same packet as the acknowledgement, the host has begun its own sequence of transmissions with its random number. Thus, SYN24 gets acknowledged by ACK25. The script is written here for you to act out as a way of checking your understanding. Volunteer one pair at a time to make the TCP handshake allowed for the class. Make up your own random numbers and respond to the other person's random number. A small note for accuracy. This script shows the acknowledger only going up by 1. Technically, the computers count bytes, not packets, so the number would go up by more. Here, for example, is a TCP header saying SYN6. It must be the first packet in the 3-packet handshake, since this computer is not yet acknowledging any packet from the other computer. Tcpip has taken care of some responsibilities. In the TCP body, we can put any payload and know that the bits will get to the right computer. We can send a sequence of packets and know that if one is dropped or miscopied along the way, it will all get sorted out without us worrying about it. We can put whatever we want in the TCP body, higher up in the layers of abstraction. For example, we use TCP/IP to send bits that follow the hypertext transfer protocol. Higher on the ladder of data abstraction, HTTP doesn't have to worry about how the packets got there or how we made sure they had them all. We can start talking about the higher level content that was transmitted. HTTP has a header and a payload. Shown here is the HTTP header. An HTTP header's first line sums it up. 200 OK. In the protocol, that's the agreed upon code for, I've got that web page, here it comes. Finally, inside the body of the HTTP packet is the HTML content. Note that the content might have been split among many TCP/IP packets. They were reassembled by the client host using the sequence numbers in the TCP header. So now we're finally high up in the layers of abstraction. We can write code in HTML to communicate content. We can add CSS to communicate how we want that content rendered. In this series, you've learned what protocols are. You've seen that they are decisions about what to do when, decisions that were compromises among competing objectives.